In this video, there's going to be a smattering of examples. For example, in this first slide, there will be finding a second derivative. In some successive slides, you will see examples dealing with higher order derivatives, implicit differentiation, and the last slide will be getting across the idea of exactly how the rules, mostly the product, quotient, and chain rules, work with derivatives. But first, let's start with finding this second derivative of this function. And so right away, I can see that I will be using a quotient rule here. I can't use one of the tricks we learned in the previous videos with there only being one term in the denominator. This has two terms in the denominator, so I cannot break this up very nicely at all. So I'm just going to get right into finding the derivative here. So f prime of x will be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. All right, so here we will have, what does this become? 1 minus x times 1 minus x times negative 1, all over 1 minus x, the quantity squared. And let's see, if we do the distribution things here and multiply these things together, this just leaves us with what? Let's see, I'll have 1 in the numerator from this multiplication. I'll have a negative x in the numerator and a positive x. So cool, I'm just going to be left with 1 over 1 minus x squared. Well, that's a good first derivative, and I think you could successfully do a second derivative by using the quotient rule again, but if you rewrite this derivative as 1 minus x to the negative 2 power, now we can just cruise along and use a chain rule instead of doing another quotient rule here. So let's go ahead and find the second derivative. The second derivative means we're just going to take the derivative of this first derivative. So I'm just going to find the derivative of this thing. I'm going to do that in some red ink over here. So f double prime of x will be negative 2 times 1 minus x to the negative 3rd power times the derivative of what's inside. And so this, I have to actually take that derivative, so I will have negative 2 times 1 minus x to the negative 3rd times negative 1, and simplifying this a little bit gives me 2 as I multiply negative 2 times negative 1, that gives me the 2 in the top. And I have to move this down to the bottom because that has a negative exponent. So this will be 1 minus x, the quantity cubed. And that's it. There's the second derivative for this function, x over 1 minus x. So here we have a situation. If the second derivative is all of this, find the fourth derivative. So for the time being, we already know the second derivative. Like, we had a function, we took the derivative of it, we found the first derivative, we took the derivative of the first derivative to get this. Well, now we just need to go through 2 more times, right? We're at the second derivative, we need to find a derivative of this to get to the third, and then the derivative of the third derivative to get to what we're being asked to find here. So the first thing I want to do here is, I know I can't use the power rule on this piece until I have x to some power that's not in the denominator. So I write, let's see, this is f double prime of x This is 2x squared minus 3x minus 5 times x to the negative first power. So to find the third derivative, and this, as a side note, is the last time we will write primes. Anytime you hit fourth derivative or higher, we just use this number in parentheses here. So I have f triple prime of x. Here we'd say f double prime of x, f triple prime of x, or the third derivative. I just need to do the power rule. So this will be 4x minus 3 plus 5x to the negative 2 power. Now, since this is not where we are stopping, right, we've got to stop at the next derivative, I don't want to rewrite this. I don't want to move this x to the negative 2 back to the denominator. I just want to keep going until I get to the derivative we're looking for. Let's see, so f fourth prime, I guess, the fourth derivative of f of x would be 4 minus 10x to the negative third power. And this is what we're looking for. So now that I'm here, now I want to rewrite this. That's because this is where we are stopping. So there is the fourth derivative, given that this was the second derivative. On this slide, I can see that we will be needing to find the second derivative for this function. And my big clue is right here. This equation is not solved for y, so we will have to use implicit differentiation. And when we do this, we will be differentiating with respect to x, and we can abbreviate with respect to x. So what that means is I can go through and now I can take the derivative of y's and any y variable, like we were taking the derivative of an x. So I'm going to have 3x squared plus 3y squared equals 27. But since we don't know what y is some function of x, or rather some expression that we can write in terms of x, it's almost like we have an outer function and an inner function here. Because I don't know what y is equal to, we have to use the chain rule here. So we can take the derivative of the outside function here, being the power rule, and then we have to take the derivative of the inside function. And because I don't know what y is equal to, we just represent the derivative of y as dy dx. Oh, and the right side here should be equal to 0, as the derivative of 27 is in fact 0. My bad. So from here, we can solve for dy dx. This is the derivative right here. So if I subtract 3x squared from both sides and divide everything by 3y squared, you'll get that dy dx is negative x squared over y squared. The 3's will cancel. Okay, cool. So we have dy dx, but we do not have this yet. We need the second derivative. So just like in the previous example, we take the derivative of this thing. And this can be done one of a couple different ways. We can either use the quotient rule, or if you like, you can rewrite it as negative x squared times y to the negative second power and use the product rule. I'm going to go through and use the quotient rule. I don't think it matters either way. You're stuck using something that is not the power rule. So I'm going to use the quotient rule. I'm going to say d squared y over dx squared will be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Again, using that chain rule here, all over the denominator squared. Now, when you're finding a derivative implicitly, a second derivative implicitly, it is not enough to just leave this. This is why in a previous video there were simplification methods given out. And here we want to keep with simplifying. So this first term will be negative 2xy squared. And on the in the second term here, I will have negative 2x squared y dy dx all over y. Let's change that to the fourth power. All right. So again, here we're almost done simplifying this, except this right here we can't leave as that. We don't want to have any derivatives being represented in this particular function. So what I want to do is I want to take this expression and substitute it in here for this expression. That way we have x's and y's, and maybe we can simplify it a little bit more. So let me write that over here. All right, there we go with this substituted in. And now I'm going to simplify this as much as I possibly can here. So let's see, what's that going to leave me with? That's going to leave me with a negative 2xy squared minus, I guess that'll be plus because I have a negative here and here. Let's see, that'll be x to the fourth. Let's see, 2x to the fourth all over y. And that's because I have a y in the numerator and 2 in the denominator. Cancel out, get this. And that'll still be all over y to the fourth. Now here I have this denominator here again. I can't have that there. I would much rather have a, let's see, no fractions here. So if I want to cancel that out, I need to multiply the top and the bottom by y. And so that means I also get to multiply this by y as well. So that'll leave me with something like this. And here's this. And getting to this point, I realized I made a sign error way back here. This would be a negative x squared, x squared, which would make this positive, which would make this positive, which would make this negative, which would make this negative. Okay, I'm feeling better about this now. All right, so then we use this simplification technique still again, where I have to factor out whatever I can from the numerator. And it looks like it's going to be a negative 2x. So this will give me negative 2x x cubed plus y cubed in an out of order sense, all over y to the fifth. And I switched around these terms here because way back at the beginning, I know that x cubed plus y cubed equals 27. So I can just substitute this 27 way down here in for that. And so if I do that, I will have a final answer here of negative 2 times 27 is a negative 54 x all over y to the fifth power. So for this particular example, it'll have the same instructions as the last one. And I'm just going to reveal the steps every, 5 seconds or so, and then I will talk about it at the end. All right, here is the final derivative right over here. I should say the second derivative right over here. And this time it's all in terms of one variable being y. The first step here, you have to recognize there's a chain rule, there's an outside function of cosine and an inside function of y. So we take the derivative of the outside function, cosine becomes negative sine, leave the inside alone. And to that we multiply by the derivative of the inside function. But we don't know what that's equal to, so we just represent that derivative as dy dx. And we solve for dy dx by dividing by negative sine of y. So here's the first derivative. And instead of deciding to run through a quotient rule here, I rewrote it as negative sine of y to the negative first power, as that tells me that I should push it back to the denominator when I'm done. And then I realize I have a chain rule here. So I have an inside function and an outside function being the power. So when I bring down the power, negative 1 times negative 1 is positive. That's why there's no negative here. And the derivative of that, I still have to subtract 1 from the exponent, giving me a minus 2 in the exponent here. And then I multiply by the derivative of the inside function being sine of y. Now, as I do this, I'm in a very similar situation that I was up here, where I have an outside function and an inside function, and I have to do the chain rule again. So the derivative of the outside function is cosine, leave the inside function alone. The derivative of the inside function is dy dx. And then I remember from the last example, I have to have dy dx rewritten as to whatever it's equal to. So I just pushed the sign back into the bottom here. And then I moved these signs of y to the denominator as well and got this. Now, seeing as how this is a calculus course and not a pre-calculus course, I would be okay, for my students, it would be okay to stop here. However, if you want to bring the pre-calculus nightmares back to the forefront of your memory, you can split this apart into cosine over sine of y, and the minus 1 over sine squared of y. And I just moved the minus over here, it just felt better there. But this ratio can be rewritten as cotangent, and this ratio can be rewritten as cosecant squared, and I just moved the negative to the front to give you this final second derivative of implicit differentiation. For this example here, we have this information. Suppose that for x and the given x values, we know the function values for f and g at x equals 0 and x equals 1, and we know the derivative values of f and g when x equals 0 and x equals 1. So here are just a couple questions that could be answered by this information here. The first of which is you are asked to find h prime of x if h of x equals this function here, or this combination of functions here. So what this would look like is, I'll do this in red ink here. So if h of x equals f of x times g of x squared, what this means is if you find the derivative, you would have a product rule happening here, and this would look like the following. We would have f of x times the derivative of what happens here, g of x squared plus g of x squared times the derivative of f of x. So again here, just analyzing this, we would have to have a chain rule happening here where g of x is the inside function, and the squared is the outside function. And so this would end up being f of x times, let's see here, this would be 2 times g of x to the first power times g prime of x plus g of x, the entire function squared, times f prime of x. So this is what we get here. And I think it would be helpful if we knew which value to substitute in here. So here this will be at x equals 0 for the first one, and at x equals 1 for this second example here. So then all we have to do is come down here and find h prime of 0. And so for that, I need to find f of 0. And so that means if the x value is 0, f of 0 is 1. So I'm going to make that substitution here, times 2 times g of x to the first power when x is 0. So when g of x over here, when x is 0, g of x is 1. So again, I have 1. Times this piece here, g prime of 0. So g prime of 0 when x is 0, g prime of x is 1/2. So here I have this piece plus, we already talked about this over here, g of 0 is 1, so this will be 1 squared. And let's see here, f prime of x when x is 0 is -3. So this will be multiplied by -3. So it looks like here I will have all of this, 1 times 1 is 1, times 2 is 2, half of 2 is 1. So this whole piece is 1, plus 1 squared is 1 times -3 is -3, and this is -2. So we can do something similar here for q prime of x with this being the function, and I'm going to squeeze that in over here on the left side of the screen. So you would get this derivative here, g of x plus 1, that's denominator, times the derivative of the numerator, f prime of x, minus f of x, numerator, times the derivative of the denominator. Again, the derivative here of a constant is just 0, so we're left with just g prime of x, all over denominator squared. Now if you go through and you substitute 1 in for all the x's here, you can do all of the little teeny tiny math pieces here and see that you will get 5/12.